Okay, so let's talk about ions. And so this next unit, we're going to be talking about ionic bonding. And so we're done with covalent, and we're moving on to ionic. So remember, covalent, that takes what type of elements off the periodic table to happen? Non-metals. So you have to have non-metal, non-metal. Now with ionic, now we include the metals. So just putting that out there that we are going to be working with both metals and non-metals. But before we get into that, let's talk about some things that we should recall, like valence electrons. So we are going to be bringing back a lot of old stuff today. Guys, remember those good old electron configs? They're coming back. All right, so valence electrons, the definition, outermost shell, or if you guys remember this term, principal energy level. Oh my gosh, the leg. Whew. Some latency, all right. And then electrons. This is what we're talking about. So principal energy level, PEL. If we are thinking about electron configuration, for example, if I just wrote it for fluorine, 1s2, 2s2, 2p5. So this is for fluorine. Those things. Now, the principal energy level, those are associated with the numbers out in front. So when I say the outermost principal energy level, I mean the highest. In our case, that's going to be everything in these orbitals. This is going to be the valence electrons because they are the electrons that have the highest principal energy level. So they both have 2, so we have to count all of them. That means there's a total of 2 plus 5 or 7 valence electrons. Because that's not in the outermost principal energy level. It's in the first principal energy level. The outermost principal energy level in our case is the second. So we count everything in the second principal energy level. We figure that out by the numbers highlighted in green. Any other questions? Sweetness. Okay, so reviewing what an atom is, these are the smallest. Neutral is the key word here. Particles of matter. So if I give you an example of carbon, who can tell me how many protons carbon has? Yeah, go ahead, Charlie. 6. So refresh your memory. To figure out how many protons an atom has, use its atomic number. So those are the blue numbers on the periodic table. So carbon is number 6, so it has 6 protons that are positively charged. Now, if it has to be neutral, how many electrons do we have then? 6. So if we have 6 protons, then we're going to have 6 electrons, therefore overall charge will be 0. So this brings us to ions. What is an ion? Well, this now is going to be charged particle of matter. So when our atoms are not neutral anymore and they become charged, we have ions. And these are created when electrons, which I'm sorry for those of you who haven't had near at home, just a refresher, protons, I abbreviate P plus, and then electrons are E minus. So created when electrons are gained or lost. Now, why can we not change the charge with protons? Exactly. If we start messing with the number of protons, that's going to change the atomic number and we're going to have a completely different element. So this is why electrons matter for all of bonding, is because, especially ionic, because this is where they really come into play. So thinking about charges, we can either have plus or minus. We get fancy names for those. So cation is going to be a positively charged ion. And then as you could assume, anion will then have to be the negatively charged ion. Okay, I'm gonna show you guys a really weird, goofy thing that one of my professors drew up on the board to help remember this. If it does or does not help you, I'm sorry, but if I were to think of a cat for cation and make its eyes little plus charges, if anything, it'll give you some nice nightmares later tonight. But cation, think of the eyeballs. I don't know that are relating anions to onions because they make your eyes water. That's a bad thing. It's a negative thing. I don't know. Okay, cation. So examples would be, for example, if I had a sodium ion, so we'll learn about these, or a magnesium ion, versus things that are negatively charged ions would be like an oxygen or fluorine. So how we write ions is with brackets, and then we put their charge as a superscript. All right, let's talk about how these are formed. So if we know that ions are created when electrons are gained or lost, do you think cations form from losing or gaining electrons? Losing. So the reason being is because you're losing negatively charged electrons. Oops, not trons, trons. So if you have a negative electron and you get rid of it, you become more positive.
So like, say you got like an element here and an element here, right?
Yep.
And this loses one.
Yep.
Does it go to that one?
If it gains one.
So then this is a cation?
That's an anion. Anions. Yes, if you gain an electron, you're gaining a negative charge, therefore you're becoming negative. Electrons are negatively charged. If you gain negative charge, you become negative. Okay.
Oh.
Yes.
So if you lose an electron, then
you're subtracting a negative. And then that becomes a positive. Okay, so I'll give you guys an example. If we have potassium, I'm going to draw its electron dot structure here with its one valence electron for funsies. How many protons does potassium have? 19. How many electrons then? 19. A potassium atom will have 19 protons and 19 electrons, but I'm going to make it lose one electron. I'm going to make it lose its valence electron here. And so how we're going to show this is, like I was doing above, is we put our elemental symbol in brackets and denote its charge. If it loses one negative electron, it becomes +1. So it still has its 19 protons, but now it has 18 electrons. So +19 plus -18 equals +1.
Oh, so it keeps the amount of protons.
Yes, because otherwise it's a different element. Awesome. Okay, let's talk about anions then. So these are going to gain negatively. I'm going to abbreviate that as NEG, charged electrons. So my example here, I'm going to use fluorine with its 7 valence electrons here. How many protons does fluorine have? 9. How many electrons overall? 9. Awesome. I'm going to make it gain 1 electron. Now how I would write this would be with F and then -1 as its superscript, because we gained 1 negative electron. And if you think about it, if fluorine gains an electron, its new electron dot structure would look like this. Exactly. And so this is the next 2 questions. Why are cations formed? Why are anions formed? What rule do you think it has to do with? The octet rule. Yes, exactly. So here, just to finish this off, we still have 9 proteins, but now we have 10 or protons and 10 electrons. Okay. So one thing I will mention here, when we start getting ions, especially anions, you are going to have this suffix that I think you guys have heard of before, of "ide." So remember from covalent naming when we were talking about fluoride, chloride, bromide, iodide, sulfide, phosphide, etc. If you see something like nitride or phosphide, or for our case, fluoride, that means the ion. Okay. So if you see, when we're talking about doing some stuff on our worksheets later, just think "ide" means it's in its ion form. Okay, so why are cations formed? We just talked about that. It has to do with the octet rule. And this is, again, atoms want full valence shell. And to have a full valence shell, that means you have 8 electrons. Now, metals, they tend to be cations because they lose electrons, therefore becoming positive, to leave full valence shell. I'm going to kind of put this in quotes underneath. And so I'll talk about this once you guys get this written down. All right, so what do I mean that they lose electrons to leave their full valence shell? So thinking about, I'm going to do this work kind of up here with the table. Let's pick on sodium. So if I think of sodium's electron configuration, I'd have 1s2, 2s2, 2p6, 3s1. Okay, so this is just the electron configuration for a neutral sodium atom. What is its valence electron in the case of its electron configuration? 1, right? It's this 3s1 because the 3 is the highest principal energy level and there's only s1, so there's only 1 electron. So if it loses this, we are left with 1s2, but 2s2, 2p6. This is now its valence shell, right? Exactly. Exactly. That's what will happen. Yep. So now you can also say, what is this the electron configuration for without 3s1? What is 1s2, 2s2, 2p6? You guys remember how to get there?
Yeah.
Yeah.
It's
Yes, neon, right? You just count up the electrons. 2 plus 2 plus 6 equals 10. Atomic number 10 is neon. Yeah. Okay, so if you're at a noble gas configuration, you got to be pretty stable. So I'm just drawing some connections here. What I mean by full valence shell and equal 8 electrons. So this happens with metals. They like to lose electrons to get there. So with anions, again, we're going for the octet rule, but they get it a little differently. Nonmetals gain electrons to fill their valence shell. To 8. So my example again, I'll do fluorine, 1s2, 2s2, 2p5. This is the valence electron configuration, or this is the electron configuration for just fluorine, neutral. It has 7 in its valence, because 2 is the highest, and there's a total of 7. How many more does it need to get to 8 in its valence? One more. So the fluoride ion would then be 1s2, 2s2, 2p6. So I'm just adding that extra electron here, okay? Any questions on this? Yeah.
So basically, the main thing is just to get it to cooperate with the oxide.
Yeah. Yep. Yep. And there's lots of different kind of ways you can think about it. So if one way kind of seems confusing, hopefully another way will start to make sense, especially the table I'll talk about on the next page. But first, I have to tell you what an oxidation number is. Sounds really fancy. All it is the ion charge. So for the problem that I just did over here, what is fluorine's ion charge? -1. That's how simple it is. Okay. Any questions before we do the table on the back? Sweetness. Okay. So we're going to tie together electron dot structures with ionic charges and valence electron numbers and valence electrons configurations. They all kind of tie together.
Wait, can you go
So
back to it?
back a page?
Yeah, like to the bottom right one. Try to get that down.
All right, I will pause. Let me know when you're ready. So connecting everything. I'm going to label my valence electrons for my sake in blue. So starting with the leftmost column, we know that group 1 has 1, group 2 has 2, 13 has 3, 14 has 4, so forth, until our noble gases we know have 8 valence electrons. And so if we think about that, I'm just going to remind you guys, if you're drawing the electron dot configuration, I'm just going to do it for the top ones here. But electron dot configuration is only with the valence electron. So I'm just refreshing. You guys should know this. You just took a test on this. So I'm just doing electron dot as a refresher, because I can use it to tie into our octet rule. So, yeah.
Like in the professional chemistry world, like does it matter like which side you start with the active fit? No.
No. Nope.
Wait, this remember?
Yes.
HE is only like 2?
Yep. Its atomic number is 2, so it can only hold 2.
That's crazy.
Okay, so now what's really cool, and a connection I want you guys to draw is, so we talk about electron configurations, right? Do you guys remember what fluorine's electron configuration just was? We just said 1s2, 2s2, 2p5, right? Because we know it has 9 electrons. This is how it fills. What is its valence shell configuration then?
Oh, they need to
Who
add
are-
2s2, 2p5.
2s2, 2p5. This is a valence shell configuration. So if we're not thinking about the specific energy levels, everything in the group will have the same valence configuration. So everything in fluorine's group will have S2P5, but obviously the principal, I'm going to write that bigger in red. Obviously the principal energy levels will change a little bit because of what row they're in, but anything down group 17 will end with something S2, something P5. Yes. Okay, and so every column has this. So in the first column, everything will end with S1 for, this is now what I call the valence shell electron configuration. Because I'm talking about generic for the whole entire column. it would be for just fluorine, but chlorine is 3s2, 3p5. Bromine is 4s2, 4p5. So I'm just leaving it generic right now. Yeah.
This is like, this probably was answered last semester, but like, why is there no P levels on number one
For the first one,
like, like there was one S2 and then it just goes straight to 2S?
there's no room in an atom for a p orbital to fit. It has to do it spatially. It just doesn't work. A good question. So S1, then we have, this is going to end with S2. Then we have S2P1. Oops, that's 2. Hold on. S2P1, S2P2. So you guys are probably picking up the pattern. We are just increasing with 1, which we should because our valence electrons increase as we go from left to right. Oh my gosh, I am writing just gibberish right now. So thinking of all of these superscripts with our valence electron configuration, what do the superscripts add up to? They're valence electrons, right? So if you add S2 plus P1, that's 3. Well, 3. So that should match. That shouldn't be a surprise there. Okay, now, how do we figure out the ionic charge? So what you need to know is that in nature, and you guys might relate to this, nature likes to take the route that will take the lowest amount of energy. Everything in nature. It just wants to take the lowest energy route because it just makes most sense. You're not just going to burn energy for fun. And so in our case, when we are looking at metals versus non-metals, or things with, I'm going to kind of label them, I'm going to circle these in green. If we think about what it means to have an octet, I told you guys that they can lose electrons to be full, right?
Yeah.
Okay. Do you think it makes sense for each of these to lose 1, 2, or 3 electrons to become full? Or gain 7, 6, or 5? What's the smaller number? Losing 1, 2, or 3, or gaining 5, 6, or 7? Losing. So these elements are going to tend to lose electrons. Therefore, what type of charge are they going to get? Positive. Lose electrons, become positive. You're losing your negative charges in life. So that being said, what's nice about the valence electrons? If you have 1, you're just going to lose that 1 valence electron, become a +1. So think of it as, if you think of the dot structures, how many dots do you have to lose to get to 8 or to be all gone? Well, for group 1, just 1. Group 2, you have to lose 2 dots. Group 3, you have to lose 3 dots. So this is where I'm pulling these charges from. Now we get to 4. This isn't necessarily going to always be easier one way or the other. We're not going to worry about group 14. Okay. But now we're going to switch gears, getting to 5, 6, and 7 valence electrons. This is where we're going to think about, in sense of the Lewis dot, I think these are helpful. Is it easier to lose 5 electrons for nitrogen or gain 3? Gain 3. If you gain 3 electrons, you gain -3 charge. Actually, you still have a question?
Kind of. Like, what is the specific name for the white elements on the bottom of the thing? Like, is there like a category that they go under?
You mean the like kind of blankish ones?
Yeah.
My hypothesis, and I have to check into it about this periodic table, the elements on the periodic table that are in white have been made in a lab. Therefore, we don't really know their natural state, so we can't color them black, green, or sorry, black, blue, or red, because they don't exist long enough to us actually to know what they are.
So, like, we don't really like study those.
They're not naturally abundant. Some might be naturally abundant, but still don't exist very long. But some are straight up made in a lab if they take one element and bombard it with particle rays until they force it to happen. I don't know. I don't know what that is. Okay, so anyway. So if we have a valence electron of 6, that means we are only 2 spots away from having our full octet. So we are going to gain 2 electrons and have a -2 charge. And lastly, fluorine is already at 7. It only needs to gain 1 more electron to be at a full octet. So its ionic charge is -1. What do you guys think about the noble gases? No, they're not going to have an ionic charge. Okay. So let's fill in this table below. So we're going to use the table that we just filled in. So you guys are going to have to look at your note sheet because I've moved down. But thinking of sodium or Na, what is its valence electron configuration? Feel free to look at the table we just filled in. What was it? S1. Okay, so the valence electron configuration for sodium is S1. So how many valence electrons is there? 1. We can just get that from our exponents. The electron dot structure for sodium is just going to be Na with 1 dot, because that's how many valence electrons it has. Now, do we think the element's going to want to gain or lose electrons? If lose. So think of it, if it's easier to get rid of all the dots, we're going to do that. What charge will it be then? +1. If we're losing a negatively charged electron, it becomes positive. All right, Mg, magnesium, what is that one's valence electron configuration? S2. How many valence electrons? 2. Then we will draw its electron dot structure. What do you think magnesium wants to do? Gain or lose? Its charge will be +2. All right, what about chlorine? Cl, valence electron config. Exactly, S2P5. So how many electrons? 7. Then I'll draw its dot structure with 3 pairs and 1 single electron. What does chlorine want to do? Gain 1. It's so close. It just wants to gain 1 more. Then its charge is what?
-1.
Yes, love it. All right, argon. What's its valence configuration?
AR.
That's its symbol. Don't laugh. I appreciate the
S2P6.
exactly. So now how many valence electrons? 8. We draw 4 pairs around it. Is it going to want to gain or lose? Neither. Love it.
So what would that be called?
Like it, or in sense, like in terms of like ions,
Yeah, like,
it's not one. It wouldn't even be called an ion.
it's just like
It's just an atom.
set in stone.
Yep. Okay, any questions on this table? How are you guys feeling about figuring out plus or minus electrons and pretty much, yeah, go ahead. Go ahead.
Oh, really?
Yeah.
Can you scroll up a little bit?
Mm-hmm.
The only thing I'm still confused is like the numbers on the bottom, the ionic charges.
So this has to do with to be a stable octet. This connects to how many electrons you're either gaining or losing. And so we know metals, we know they tend to.
Oh, wait, no. I got like the plus and minus mixed up. Never mind.
So it's not number of electrons, but it's the charge resulting from
Yeah.
gaining
So
and losing.
for the first period, like with +1 to like actually losing an electron.
Yes.
Oh, okay.
But be careful, it's called a group.
Oh.
Okay. All right. Periods are rows. Okay, so yes, again, recapping. If you have fewer than 4 valence electrons, you're going to lose. Greater than 4, you're going to gain. But also remember, metals like to lose electrons. And where do the metals live? On the left side with the lower number of valence electrons. Right side, non-metals live with the higher valence electrons. They like to gain. Also, from last unit, could you guys tell me about a periodic trend with the non-metals. What was fluorine? What did it have the largest value of? Exactly. Yes, Leo. Electronegativity. What is electronegativity? It's attraction of what? Electrons. So it makes sense that these atoms that really want electrons, they're going to gain them. So I'm giving you guys some more tools to think about for this. Okay. Now we're going to talk about how I'm going to mute the TV. Okay. How these ionic bonds form, we're going to actually write it down now. Probably. Okay, so how they form. So the video kind of hinted at it, but let's actually get some stuff written down here. So we learned that our metals easily lose valence electrons to nonmetals. So ionic bonds are between metals and nonmetals, and they happen from metals giving their valence electrons to nonmetals. So in the example we just watched with table salt, NaCl, sodium gave its 1 valence electron to chlorine, who already has 7. Now chlorine has 8, and underneath that valence shell of just 1, sodium has a full shell. So metals, if metals are losing electrons, what do you think they become? Cations or anions? Cations, awesome. Because if you lose a negative, you become positive. That means our nonmetals become anions, which are negatively charged. So what's really neat about these ionic bonds is that the ions are held together by electrostatic force of attraction. So who here has taken a balloon and rubbed it on your shirt and stuck it to something? Yes, at least seen it done. That's the same idea here, that the balloon gets attracted to something, but it's not physically connected. You can say the same thing about ions and ionic bonds. They're very attracted to each other, but they're not physically connected. Okay, and then the last thing to just say one more time is that each ion is now stable, which we can say that it has its full valence shell, or what's that other fun word we use a lot? Means 8. Octet. So, any questions on how an ionic bonds form? Okay. So the last thing we'll go over quickly here is that there's these properties of ionic compounds. Well, one is that when they're at room temperature, they have what's called a crystalline structure. So they're a crystalline solid at room temp. And so if I'm thinking of ions, if I have a sodium, and then that's plus, chlorine will be negative, and then a sodium, and then a chlorine, they just kind of line up next to each other. NaCl, NaCl. So they just start lining up next to each other because the positives attract the negatives and the negatives attract the positives. So I have this little picture here in the corner. Then I also have this in classroom example of what it means to be a crystalline solid. So they line up very nicely where even if you take a special fancy x-ray and look at these in solid form, it'll look just like this. So they line up where as if you pretend the sodiums are the whites, the chlorines are the red, line up really nicely next to each other. So, number 2, they have high melting points. For example, we've been talking a lot about sodium chloride. Anyone want to take a guess at its melting point? It's okay if you guess in Fahrenheit.
I'll say 89 Celsius.
1,474 degrees Fahrenheit salt melts at. Isn't that crazy? And so this is an ionic. Remember how we talked about covalent were low melting points? Think of water. What is water's melting point?
212.
That's boiling. 32, exactly. we know that ice melts at 32 degrees Fahrenheit. That's a covalent compound. Compared to 1,474, that's pretty big. All right, last thing. They conduct electricity, but this is only when melted or aqueous. So you guys are probably like, what the heck is aqueous? It is just a fancy term for dissolved in water. Exactly. So I will show you guys another couple cool videos here.
What's that word?
What's up?
So the crystalline solid, that's like that?
Yep.
That's like the bottom.
Exactly. Okay, so now we're gonna watch another beat video about, so this is showing how salt in a solid state will not conduct electricity. And so for those of you at home, I'm gonna mute myself, but this video doesn't have sound anyway. Okay, you guys have such like creative minds. I enjoy it. Okay, so the last thing I wanted to say, this easily could be a test question. All right, for those of you listening, it'll help them. So if I were to ask a question like, do ionic solids conduct electricity? What would you say?
Yes,
No, ionic solids do not conduct electricity. They have to be melted or aqueous or dissolved.